Hi everyone, my name is Howard Zhang and I will be presenting on the paper titled WeatherStream, Light Transport Automation of Single Image Deweathering. The field of deweathering aims to remove weather effects such as rain, fog, or snow from images. As the effects of weather frequently result in information loss, many methods used to tackle the problem rely on data-driven deep learning. A recent paper titled Not Just Streaks Towards Ground Truth for Single Image Deraining has shown that methods trained on time multiplex data perform better than methods trained on synthetic data. However, time multiplex data relies heavily on manual human labor for collection and is therefore not scalable to large sizes or multiple weather conditions. Our paper proposes a method of automatically collecting time multiplex image pairs that scale to multiple weather conditions by leveraging a set of light transport principles that are adhered to by the rain, fog, and snow weather conditions. We validate the effectiveness of our dataset by retraining multiple SOTA models and showing better results for WeatherStream retrained models across the board. So why do previous methods trained on synthetic data perform poorly? And if they do perform poorly, why use them at all? The effects of weather are highly volatile and physically complex and can be dependent on many uncontrollable factors such as camera parameters, atmospheric pressure, and even geographic location. Ideally, we could collect a vast amount of real image pairs that would cover the gamut of all of these parameters. However, data collection for deweathering falls prey to the problem of the ideal ground truth. A majority of data-driven techniques require image pairs of scenes with the exact same composition and lighting, with and without weather effects at the same instance in time, which is physically impossible to capture, hence the reliance on synthetic data. However, as seen in the images found on the left, many synthetic images are unable to mimic the complexity and variety of real-world weather shown on the right. A recent paper titled Not Just Streaks Towards Ground Truth for Single Image Deraining focuses on collecting these pairs by instead trying to capture the magic moment right when rain is about to stop, thereby capturing both rainy and clean image frames only minutes apart. They then manually sift through pairs to ensure image quality. We can see in the bottom data samples that collecting pairs through this method results in capturing complex real-world weather phenomena while avoiding other artifacts that arise from the small time difference. However, scaling the dataset to larger sizes and multiple weather effects is intractable with manual labor. Hence, we introduce WeatherStream, an automatically collected dataset with minimal human effort. This dataset is 6 times the size of GT-Rain and covers the rain and snow weather conditions, along with their associated veiling effects. To collect these image pairs automatically, we follow a set of 4 principles, each with their associated filtering block, which I will get into now. The first principle is background conformity, which states that the objects in a suitable paired scene exhibit no motion and color constancy. This simply means that the underlying scene with and without weather effects must remain the same, which necessitates that no moving objects be present in the scene. Our next filtering step is particle chromatic variation, which states that rain streaks and snowflakes exhibit isotropic derivatives in RGB pixel intensity. This is a result of the motion blurring effect of rain streaks and snowflakes when captured by traditional cameras. This motion blurring effect, along with the typical bright compounding internal and specular reflections of weather particles, results in a neat linear relationship between the difference in pixel intensity between the clean and degraded image and the pixel intensity of the clean image. Since this is true for all 3 color channels, we can leverage the isotropy of the RGB pixel space to determine if a pixel is on a weather particle or not. Please see our paper for a more detailed mathematical proof of this relationship. The third filtering step is scattering-dependent blur, which states that a degraded image is blurrier than a clean image due to scattering effects. Depending on camera and weather particle size, scattering media can be formed throughout the scene. In most instances, this is represented through single scattering formulas, with a convex relationship in radiance between the air light and the underlying scene radiance. However, a more accurate representation would include multi-scattering effects as seen in the diagram on the right. This is commonly formulated as a convolution with an atmospheric point spread function, which leads to a blur effect throughout the image. Detecting this through frequency analysis can help us in determining whether an image pair is suitable for our dataset. The fourth and final filtering step is illumination consistency, which states that the ambient illumination should remain consistent despite weather effects. Unfortunately, since we are unable to control illumination stimuli throughout the scene, and changes in illumination can be confounded with the presence of scattering media, we opt to use a deep learning model trained on a smaller seed dataset which conveys enough scene understanding for a coarse binary decision boundary to assess if the illumination is consistent between frames. After passing all these filtering steps, we have our final collected dataset. The following are a few samples from a variety of geographic locations with a variety of different weather effects and camera parameters, resolutions, exposure time, etc. The following samples display outputs of our pipeline with some of the filtering steps removed. As you can see from the left set of images, removing the background consistency check results in obvious object discrepancies between the clear and degraded images, with a train in the left image pair and a car in the right image pair. In the middle set of images, we see what happens when the illumination and blur check, filtering steps 3 and 4, are removed. We see obvious differences in the illumination between clear and degraded frames. Now that we have our collected WeatherStream dataset, we can see some of the results of retraining state-of-the-art models on our newly proposed dataset. As we can see from these outputs, images output from models retrained on WeatherStream perform much better than those trained on synthetic datasets. In fact, for some models, retraining can see a jump of up to 2 to 3 PSNR as compared to a synthetically trained model. Please visit our webpage for more information regarding our project. Thank you.